And I will share. Okay, so this is the Ontology Summit 2020 Fall Series. The meeting today is on September 18th. And what I have done is attempted to kind of summarize some of the issues that were raised, some of the comments that were made in the first two sessions. No doubt I have missed some of the things that were discussed, but hopefully this will be a good point of departure. Oh, man.
Good morning.
Good morning. I think this is not working, so let me try a different.
Oh, I was getting it. I don't know what happened. I was getting your slides. Yeah.
I think Ken is trying to change the scale.
Change the scale.
Why?
Seems to have lopped off some of the things I had on the slides.
If you escape, if you do full screen and then escape.
That's not the issue, Ravi.
No, the font is messed up.
Oh, no, that is, your font is too large for the area of the slide. But I would request you keep it like this because we can really read it well.
Okay. All right, so yeah, I'll leave the large fonts.
Thank you.
So now what Jans told us, we began by saying, good luck trying to find a definition on the web that is not ideology or vendor-based or very application-specific. However, he did attempt to give some idea, and I'll have that on the next slide, of what he has seen proposed for what knowledge graph means. He also proposed an architecture which had a number of layers, a collection layers, and that's where ontology appeared, then cleaning, then storage, and finally applications on top. But then when he actually showed us what was happening in his own, the applications that were developed at Franz, it was pretty clear it's a lot more complicated than that. He showed a series of slides where he showed how the different components interacted with each other.
Hey, Kenneth? Kenneth?
Yeah.
In that list of items you have for proposed architecture, that's an application architecture, isn't it?
Yes, it was definitely application architecture.
As opposed to just the architecture of the knowledge graph by itself.
Well, we'll get to the next slide.
Okay.
And then we'll see, because the way he
I'm sorry, I take my words back. I can't see the bottom part of the slide. So you have to do some trick to fit that within the slide area. Reducing font can do it, or by clicking fit, there is a function saying fit to the area. Either way.
Yeah. All right, let me try something else.
Yeah. You have a PDF of it?
I posted the PDF. It's on the meeting page.
So maybe we can just download that.
Let me try one other way of getting at it.
If you just load that PDF, that's what we need. It's fully fitting in the PDF. I see that now. Okay. So you can kindly show that PDF. That's it.
How does that look?
Well, let's look at the next slide and see. That's where the problem started. That one, first slide looks fine. Oh. We just lost the PDF.
You lost the PDF?
Yeah. Oh, now we see it. Okay. Well, it looks like everything's on the slides. This is slide number 2.
There it is. There, the font is okay.
Yeah. Okay, good.
All right. As I said, the actual architecture is much more complex as they use Prolog for doing their reasoning. So it's basically a programming language. And I imagine other companies that do this are also using programming languages ultimately for their reasoning. But they use many other tools as well, machine learning, natural language processing, and so on. So that led him to give as his definition, a knowledge graph is a system that tries to know and learn everything it can about an entity of interest to improve.
Whoa.
Internal processes, customer experience, health. So taken right off one of Jan's slides.
Well, I would certainly disagree with that one. Nice. It's a nice goal, aspiration perhaps, but learn everything?
So
yeah, we're into AI now.
Yes, very much so. And then he went on to say it always includes a semantic graph, ontologies, taxonomies, always includes identity management and a smart integration of silos of information. So that there are all sorts of tools that people use for that. It nearly always includes machine learning, natural language processing, and text classification.
No.
And then he mentioned it all commonly nowadays also includes speech recognition.
You know, after hearing his presentation, this would describe the projects he's worked on more than a more general notion of knowledge graph, or you could say it's knowledge graph in the context of his company.
Yeah, I suppose that's one way of interpreting it. But he did make some observations that I think are helpful to us.
Mm-hmm.
Graph databases are now accepted.
The first bullet is oversimplification, but it's a nice goal, as Todd said. For example, the first bullet, it always includes. Well, can we think of a system where you don't need to use ontologies and taxonomies and just use text and extract graph from that? Sure, entities you need, but you don't always use ontologies and taxonomies, although it is again desirable.
Well, I think what he's saying is that because he did go to a number of knowledge graph conferences. And I guess by saying always includes, it's in all of the cases that he has seen. It includes these.
In mathematics, we have a concept of minimum irreducible representation. And so related to that are the tuples. So are these all the three things that if they are not there, it is not a knowledge graph? Probably Google or others can confirm it whether it is or it is not.
So this is Ram here again.
Yeah, Ram.
I'm sorry, I'm cutting in and out. I'll be going. So in any case, I think one of the fundamental things with knowledge graphs is that what is new. Okay, so if you look at most of the discussion that even Osman has made and other people make, is a semantic graph. Yeah, it has ontologies, it has taxonomies, and it has got Bayesian. People can talk about Bayesian networks, which is also a kind of a knowledge graph. So the key question is that if you carefully look at 1980s, in terms of the representation schemes, even SOA's conceptual graphs and those kinds of things. They are all 1980s stuff. So what is kind of new now, that why is this becoming very important? And I think it's like the neural networks. What happened is that in 1990s they were there, but then what happened is because of the deep learning things where the processors becoming very fast and many layers came into the picture, and neural networks, that's the new part of it there. That is multiple layers, and you can achieve things which you couldn't achieve before.
No, Ram?
Knowledge graphs. Pardon?
Ram, I think there are some simpler explanations as to why knowledge graphs are more popular now, or more useful or needed. And it's one is just the amount of information that's floating around, and secondly, the things that people expect to be able to do with that information.
No, let me just finish my.
I'm sorry.
Sorry about that, Todd. But the thing, what I'm trying to say is that we need to provide. I mean, it's a lot of times you know it, I know it, kind of thing. But who else knows it is the issue? Okay. For us, we have been in this field. We believe that it's an important area. Okay. And also, so what we need to articulate, what I'm trying to say is to what we need to articulate is what is the difference, and you just articulated some points. So we need to make it very clear how we need to, like why knowledge graphs now, and what is that is, there are two things that are happening. One is the representational schemes itself are improving, and the hardware also is improving. How are these two things combined together so we can also do things which we could not have done, like common sense knowledge? Because Psych was one of the attempts to common sense knowledge, and he is putting in lots and lots of information over years and years and that. And people can claim, why not? Why don't you people use Psych? So, I'm sorry, Todd.
No, that's okay. There's lots of reasons people don't use Psych. One, it's very difficult and complicated. But even so, with the notion of knowledge graphs, as was pointed out, there's no useful or commonly accepted definition. And if you look at some people who are using knowledge graphs, the notion of ontology is just foreign, or at least not immediate in their work. So you can build a knowledge graph that'll do your job in that it has some semantics representation in it, but from an ontological perspective, it might be absolutely disastrous. But still, it does the job for what they need.
Or they could have a thing they call an ontology that be equally disastrous.
But again, it meets some needs, and one of the drivers for those needs, as I mentioned, was just the amount of information that's out there now. Everyone collects so much stuff. What do you want to do with it? And in order to make use of it, you have to have some semantics.
Yeah. So Todd, what I'm saying is that there are a lot of schemes which have already been developed, but now there's something else which is happening that can make this more practical. So what is that? That's something that is happening.
I know what it is. I think you people have just articulated it in a nice way, but to say that whatever we were doing through the so-called conceptual graphs that you described, SOA and others wrote about, and now we know since the 70s the machine learning exists. What is new is ability of the machine learning to tie to rest of the knowledge around the subject or entity of interest, and then adding to that the external information that we have about that entity. So it's essentially AI.
No, but is this facilitated by better hardware mechanisms, better representation schemes? What is this being facilitated by?
There's software. By software.
What kind of software?
Definitely.
Well,
the three things that are necessary are some kind of the training set, like this cup. So the cup's image is shown in this graph. The visual representation of this graph has similarity to this cup. So you use Bayesian formulae on the probability of occurring, and you use the training set, which means the external world from where you can get all images of the cup and see if this object described in this knowledge graph is actually the cup.
I think the next slide gets at more of the points that Ram is making. That I think this one slide 3 has issues that we could disagree with, but 4 is more straightforward.
4 was just some observations that, that it appears that graph databases are indeed being accepted because they can deal with complex semantic data in ways that the more traditional storage structures do not. Apparently.
Well, I'd like to make a comment about that. The point is that there are two kinds of software. There's software for anybody to just pick up and use immediately. Things like there are things like Twitter. Even somebody like Trump can use Twitter. I mean, that's the lowest possible denominator. And then there are things that are designed for professionals to use to develop software. So the things that Jan Sassman was talking about is that their company develops software for professionals who develop tools that end users can develop. And well, their company also serves as consultants, so they work with various people to design software for their company which uses these knowledge graphs. So there's no such thing as a general purpose knowledge graph system that anybody can walk up and use. Now, there are various things that somebody who is a programmer who understands software design and development, there are lots of packages that use those knowledge graphs. Now, the point that I make about the graph databases as the best technology, no, that's pure nonsense. A graph, I keep emphasizing, there's no logical difference between a graph database and a table database. They're identical in what they can store. The difference is what software do you use to access them, and the only people who access a graph database are professionals. The only people who access a table database are professionals, and the only difference between them is which kind of program those professionals are choosing to use, what algorithms they use. So that point about saying that graph databases are the best technology, no. I mean, if you look at spreadsheets, people love spreadsheets. A spreadsheet is nothing more or less than a table database. And people love table databases because they're people like those spreadsheets because they're relatively easy to use by people who do a lot of accounting and other kinds of stuff. So the point is, scratch that word best. The only thing is, logic is the way you represent data of any kind. The only question is which subset of logic are you using, and then the only question is which tools are you using to allocate that. So scratch the point. There's databases simply mean some logic representation to store data. That's all it means.
John, can I ask what is the example of a graph database?
RDF. Okay.
RDF. Okay.
Yeah, and then RDF is just one subset. Is just the basic subset, namely, there's only two logical operators: exist, conjunction, and existence, and that's all you have. Then when you have negation, that gives you full first-order logic, and the conjunction and existence, that's basically what you have in a relational database. That if you have a line in a relational database, every row in a relational database maps to a tiny little graph that contains one relation and then the one relation name and then the items that are linked to it. And you can download everything from a relational database into a graph database. That's a trivial operation, pure syntax. There's no semantics involved. You can map a graph database to a table database and vice versa. No difference whatsoever. The only point is that the graph databases are better for data in which there's lots and lots of blanks in your database. So if you have a table database in which almost every node is, every space in your table is a blank, you're wasting a lot of storage, and you probably would be better off using a graph database. So graph databases are better for storing data in which the tables are mostly have lots of blanks in their rows and columns. So, and a table database is better for one that's filled up. That's the only difference.
Yeah, that's great, John. Could you?
So that means you just described that method.
Could you, somebody capture that in the chat? I don't know.
Well, that is my problem. That's why I'm requesting you, Ken, that we record it. So that we don't lose such good.
Well, I have made that point a million times. Well, not a million times, but hundreds of times in different different papers and different slides on my website.
Right.
I keep saying it again and again and again, and people just don't get the point. Logic is the only way to represent data.
That. It's good.
But
going
now
on
can
with
I ask it? 1 minute, sir. I want to ask, what you described, John, is that in this sparse data table of the database, the only existing data are either a link to a relationship or to an entity or both.
Well,
the rest of it is blank.
In logic, all you have are relations and the things that the relations relate. So you just have, in first order logic, you have two kinds of things. There's the relations and then the things that the relations relate. And that's all there is. And there's nothing more. And that's basically, first order logic is the foundation for all the databases you can find. The only thing is a graph database is more storage efficient if you have sparse tables. If you have a table in which most of the rows and columns are completely filled up, it's more efficient to store it in a table. If you have a database in which most of the rows and columns are empty, then it's more efficient, storage efficient to put it in a graph. That's all there is to it. There's nothing more. If you know logic, everything else is obvious. If you don't know logic, everything else is a mystery. So my point is, learn logic. If you don't know logic, you can't do anything rational.
Okay, great.
Wow.
So let's move on. There's a little more.
Can I make a point on that first bullet? He doesn't say that they are the best technology. He says that they are accepted as the best technology, which to some extent is it's just a state of the market rather than anything. This is it's part of the zeitgeist that people are interested in graph databases and think they are the best technology to store complex semantic data.
Right. It's good to point that out, that he's not saying they are the best.
Right.
They're saying that in industry they are accepted right now. And they also accept taxonomies, but they're still scared of ontologies. So
yes, they are.
Yeah, and I guess you could say people are still scared of going all the way to first order logic. Interesting observation that entity extraction and natural language processing is nearly a commodity, which is quite a difference from what it's been in the past, where this kind of processing was still considered quite difficult. And now we're seeing the same things happening with machine learning and advanced analytics. So then some of the comments that were made at the first session, there was a question about representation languages that a number of people raised. The answer seems to be RDF and OWL2, but that's I'm not asserting that that's true. Todd, you asked about foundational ontologies. It doesn't seem to be, it isn't clear that they are actually used.
Yes, definitely very clear.
You think it is clear they're not used?
Oh yeah. If you look at some of the work out there, especially things that are put out there as we're using OWL. If you consider some of their constructs, they're problematic.
I see. Okay, so
That is because of the way RDF is mapped, or because of the way UML and all connected. What is the source of the problem, Todd?
In the context of using foundational ontologies, people, I think, don't know about them. And if they do, it can be more difficult to use them. I mean, if I just take a nice list of terms that are commonly used, say, in my domain, and I think I can organize them in a coherent fashion that's useful for what I need to do right now, why should I go to the extra effort of doing the ontological analysis or trying to map them to a foundational ontology, which is going to introduce a lot more quandaries than I may have time to answer? It's more difficult to use them. The benefit of using them is you get a more extensible product or result that has a longer lifespan for usage. So it's an engineering trade-off, right?
Yeah.
I got
Well,
lost.
that definitely comes up. That's the, yeah, Marc Underwood.
I hope, Ken, you are recording now.
Yeah.
Okay,
Ken has been
thank you.
posting the audio recordings, Bobby.
Yeah, audio recording is fine.
No, but he posts them, so they're available.
Yeah, I post the recording.
Yeah.
Now,
Yes, he does, and I can't see it. Usually I can see it on the Zoom with the red button, something showing the recording is on, but I'm not able to see that today.
It's there.
You're not
Okay,
showing that.
then fine. I apologize.
No,
I apologize. I spoke too soon.
okay, so let me get on. There were some interesting questions that were raised that I don't think we fully covered. So that's where Gary asked what ontologies are actually used. So there are a lot of ontologies out there and ontology repositories. It would be an interesting question. I mean, at least there's a good ontology repository for biontologies.
Kenneth, we could refine that question to say, what ontologies are being used in what domains? So as you mentioned, the bioportal has a huge number, and they seem to be used a lot. But in other domains, there are fewer ontologies, and whether they're used or not, I don't know. Perhaps Gary knows. You know, for instance, in sensor networks.
So am I remembering correctly that Jans answered the questions at one point saying we made our own ontology? I mean, so then the question then becomes why? What's wrong with the existing ontologies that you didn't use them?
Well, I think his projects, part of his projects were to be able to create the ontologies out of a corpus of material and then to be able to extend them.
So using the first order logic, if we are able to define entities and their relationships, obviously triples fall in that category, then he is using ontologies in one way or the other, isn't he?
No, I think.
And his entire range
using
of products that work with allograph, Franz works with Sparkle. I have used a little bit of it. So it does use ontologies in a way, does it not?
No,
Well, so on this issue of using ontologies, it seems to me, if I take sort of Todd's position about the entities were sort of what they needed, they took them from where they were, is that this is using ontological engineering in a different way. It's essentially creating them on the fly from some data that's out there, as opposed to looking at the existing ontologies that might relate to the data. And therefore, you're going to get all kinds of silos of ontologies. Everybody is taking data, looking at different data and sort of building from that, as opposed to trying to harmonize these things over time.
Well, in Fibo, we try and identify the as many high-level abstractions as possible, so that when we start bringing in other things like real estate or insurance or something, the building blocks are still there. Obviously, there's still a limit to how abstract you can go.
Well, that's what the foundational ontologies is supposed to help with.
No, that's not going to happen. There always has been an open-ended variety of different ontologies, and a top-level ontology is nothing more nor less than the intersection of the compatible parts of all of the sub-ontologies. And when you look at everything that exists in the world or on the www, you'll find that the intersection is just one single node, the top node entity. So the point is that interoperability is the fundamental issue about ontology. A top level on the only ontology everybody can agree on has just one node called entity or T or top or whatever. That's the only commonality, and interoperability is the fundamental issue of ontology, and there is no way that that these top levels can ever unify everything. That's just impossible. And I think this whole project that I keep trying to get a standard top level is just meaningless. It's not possible. The only issue, the primary issue, is interoperability. And if you can't handle interoperability, you've got nothing.
Yeah, but it keeps Barry occupied, John.
Right, and that is not a good thing.
Well, interoperability is a very complex problem, and in general, the best we can do is solve it for some set of domains, some constraints on what you want to have interoperate.
Well, there are some people have done a fairly good job on it, and Psych has done a pretty good job on accommodating an open-ended variety, but they end up having, well, the last count I remember hearing, they had 6,000 microtheories, and most of which were incompatible with one another now, or inconsistent with one another. Now, Lennet does not like the word inconsistent because it raises red flags and flashing red lights in everybody's mind. But the point is, that's the only way you can do it, because the world has an infinite number of inconsistent ways of looking at it, and it's got to be inconsistent. On the other hand, there is a single world, so there are things that you can find commonalities, but those commonalities are at such a high abstract level that they're, for practical purposes, they're not really that useful, and you end up having to deal with the low-level things. And if you want to say, how do you deal with the low-level incompatibilities? Well, you just deal with it the way our dictionaries go, and you just look at any definition and you see a long list of different definitions for each word, and that's basically what you got to deal with.
Okay.
May I interject something?
Yes.
Yes, my name is George Hurlbert. I'm in there as none such one. And I tend to be a student of graph theory, and I believe there is a difference between graph and relational. I accept the idea that logic is the unifying factor. However, in the graph environment, you can get metrics, and those metrics define the unintended consequence of the internet, namely networks. And the graph is much more oriented towards describing networks of things, networks of entities, and/or networks of concepts. The Europeans are pursuing the area of networks, which adds even more dimensionality to the notion of a singular network, that is, a singular domain, such that there is some tendency through mathematics, graph mathematics, to look at the interaction of interacting networks together, and thus some possibility, at least, of working towards a higher level ontological view of the world.
Okay, basically, I agree with that. I agree with that point. And the thing I would back up and say, yes, networks of networks and networks of graphs and also a thing. But when you boil it all down, you get down to the level that you're still representing everything in logic. And in logic, you still have basically, in first order logic, you just have relations and things that they relate. Now, the kinds of procedures that you're talking about, I think, are very important, and I would say that what they're doing is establishing metrics and for getting approximations so that you can say that there are these, let's say you pick a simple word like, okay, automobile, and there's a huge number of different ways of thinking about automobiles, from the way of manufacturing them, selling them, using them, and anything else, and different ontologies for an automaker, for an auto dealer, for a user will be very different, and you can use various strategies for finding the commonalities so that you'll have a very general definition of automobile, and then you'll have sub-definitions and specializations for every possible use. And but basically, when you get down to it, you can flatten it all out in just one flat level, and the point is that that flat level will be so immensely huge that it's very hard to get a grasp around it, so that what you do is then look at various contexts. So you look at it just from the context of the auto dealer, it's a lot simpler because a lot of the things that the auto dealer doesn't care about are gone. But then if you look at it from the point of the auto mechanic who fixes cars, you have a different view, and they have simplified it to the kinds of things that they do. And then you look at it from the car user, you have a still different view. So the point is, there is an immense amount of stuff out there, and it's possible to relate them, but you relate them with a variety of different strategies that give you ways of dealing with it. And so I would say that that example there that you just cited is what I've been trying to say. It's a strategy for dealing with handling the interoperability among a diverse number of views.
But John, that's not a reason not to have upper ontology. It's a reason not to have a realist upper ontology, because we all conceptualize things differently in different contexts. And so it's being able to reflect that and the different ways that the world is carved up in different data sources and management reports and so on.
I completely agree. And the thing is that you need to have at least two different, from your top level entity, you need to have a split between what exists in actuality and how do you talk about it. Absolutely. And that can be your logic, your language, or whatever. You need at least that two-level split. And that's the kind of thing that I say is the fundamental flaw of BFO. They have this idea that the only thing that exists are embodiments. And so down somewhere deep below their embodiments, they have embodied signs. That is that in their ontology, and that's the worst possible place to put it, because that says that the abstract is an abstract thing like a number or a name exists only as an embodiment of it, so that and you can only have a finite number of embodiments, so you can't talk about number theory because there's an infinity of possible numbers, and you can't represent all of them, and that kills the whole idea of just a realist only. You must have the something called mathematics or signs or abstractions on the one side, and those represent all the possibilities. And there's an infinity of possibilities, of which only a finite number can ever be implemented. So you must have at least a two-way split between your abstractions and your implementations. Another way of talking about that is your possibilities and your actualities. The actualities are always a subset of what's possible. And then you also need a third branch, which is your necessities. The necessities are the laws that govern how everything fits together. And so you at least need three branches. One way that you can handle that with just two is to say that the laws themselves are language, so that you take the necessities are the possible axioms of all your mathematical theories. So you basically have a mathematics branch that has all the possible patterns, all the possible schemas, all the possible entity types, the infinity, and not just a countable infinity, but infinities of infinity. And then on the other side, you have the actualities or the realities or the things that actually exist, and that's always finite. And but if you don't have that two-way split, you're stuck. You can't get anything.
Absolutely.
Would you maintain that a network is essentially a sparse matrix? And that
Exactly.
Sparse matrix defines exactly what the context is within a given domain. But if you broaden that to the network of networks, there are still metrics available that are emerging that will begin to define the higher level environment. According to the,
Yes, yes, I enthusiastically agree. And so that if you have networks of networks, for each network, there would be you can have a suffix like, say, network ABC, network BDF, and so on. And then if you have a network of networks, you can always expand that into a single network, an immense network in which all of the sub-networks are embedded. So that, on the other hand, I enthusiastically agree with the importance of contexts and partitioning into, well, Psych calls them micro-theories, and they have 6,000 of those. And at least that was, a few years ago, they had 6,000, and they probably have more now. And the point is that you must have that partitioning method for dealing with just the context that you're interested in for your particular application. So,
exactly. Sorry.
Yeah. So I enthusiastically agree with both of you.
Okay, so Zachary, who isn't here, I guess, brought up the issue of persistent identifiers, but actually, Jens Osman did mention identity management as being one of the features of these knowledge graph systems. So that's certainly does seem to be part of what knowledge graphs consist of. Then the Marc brought up pragmatic and engineering issues and compromises. Marc, you are here. I don't know if you want to continue discussing that, but
well, I could just kind of this is pretty low-tech conversation about it, but often we find, and I just got through a summer-long semi-experiment with an intern in which we were trying to build some loose ontologies around cybersecurity tooling. And the pragmatics about this, dealing with people who are non-experts in ontologies or even in, you know, the adjacent specializations like knowledge engineering, are that they usually are starting with other representation frameworks that are non-ontological. So the bridging that you need to be able to do from those often graph-based representations like flowcharts, sometimes it's something more better fleshed out than a flowchart. And you know, there's a lot of standards work around other kinds of representations that I think, you know, following John's theme here, you probably could boil them down to logic in their best form, but often they remain as kind of informal checklisty kind of things that are semi-graphical. But that ends up being the starting point for the non-experts. So the on-ramp, if you want to think of it this way, for the journey of building real engineering solutions tends to be through these non-ontology knowledge graphs, and maybe even calling them knowledge graphs is a stretch, but those quasi-visualization, quasi-knowledge-based structures are super powerful in getting people on board into a common way of thinking about it. So I think of these things as maybe not just adjacent, but like preliminary setting events or context setting for people who are going to be part of a project. So that's what I was thinking in terms of the pragmatic and engineering aspects. And the publications that have come out over the last 12 to 18 months in the ACM and IEEE journals, which are the only two that I really read with regularity outside of the ontology space, tend to be along these kind of practical engineering uses of it, as opposed to, you know, heavy duty machine learning or other kinds of approaches to this. And I think that's probably typical of the kind of compromises that I was alluding to here that people make when they're trying to build something. So that, in a gist, that's kind of where I was headed with this, is seeing some value for the lesser integrity, if you want to call it that, representations that these other graphical representations that you find in software engineering can offer.
Yeah, I would say that I enthusiastically agree with you. Also, I love visualizations, and I think visualizations are extremely important, and they're important across the board, from the most informal to the most precise. And visualizations and logic go together like hand in glove. And the point is that if you have a visualization that is any kind of a diagram in which you have any sorts of labels of any kind that are connected in any sort of way, you can map that also. If it's discrete, you can map it to a logic. If it's continuous, you map it to an image. But the thing is, you need those images, you need those graphics, and they're needed for the most theoretical thing. The mathematicians and physicists in the most abstract and most highly advanced forms of science, they love good diagrams. And Feynman, for example, Richard Feynman, who was one of the Nobel Prize winners and one of the people working on the Manhattan Project and all those things, Feynman loved diagrams, and he invented diagrams for representing the interactions of all these molecules. And there's not just one single form of diagram, there's an infinity of possible diagrams, and they have to be represented, and they're the fundamental ways of thinking. Diagrams are closer to human thinking, both for the most abstract mathematicians as well as for the most mundane, sort of informal kind of person on the street. You need those diagrams, and I strongly emphasize the importance of them. But again, when you got to represent it on a computer, the computer itself, any digital computer, can be completely specified in first-order logic. Every program that runs on a digital computer can be completely specified in first-order logic, and it doesn't matter how many levels of diagrams or whatever there are. When you get it down to the computer, it goes into bits that are all represented with zeros and ones, and that's as Boolean as you can possibly get. And the point is that, yes, you need all of these things, and you need to represent them, and that's fundamental. And so you have to face that you're going to have an open-ended variety of ontologies that are specialized for every imaginable possible way. And one of the things I also emphasize is that everybody speaks some natural language, and so that you need to have ways of relating what they say in their ordinary language, in which they visualize in their preferred form of diagrams or imagery or whatever, and you need to relate that to what you implement. And that's where the hard part comes in, relating the way people think. People think in diagrams, they think in language. Those are the two complementary ways of thinking, and you have to relate them down, all the way down. It gets down into the computer, it's all zeros and ones, and along the way you have many, many levels. And I strongly agree that you need semantic distance measures for grouping things, for finding things, for indexing things. All of that is very important. And the thing that I am unhappy about that that proposed ontology standards for ontology is that they have just ignored this huge amount of complexity, and they're saying that there's just one little idea that somehow this top-level ontology is going to solve everything, and the simple answer is no, it won't. I mean, Psych is the closest thing there is to developing that project. They started off in 1984 with the idea that they would have a single top-level a single top-level ontology, and then they would break it down. It only took them 5 years to discover that a single top-level ontology is not possible, and they had to break it down into context and micro-theories. And then the person who invented them was Guha, who was the associate director of Psych, and he and Lennart got into arguments about the details, and Guha split off, and he's the guy that invented RDF. And he also admits that RDF is only a basic starting point. And then he also was working for Google, where he invented schema.org. And that's another sort of ontology-like thing. And none of those things have ever been the final solution. And my point is there is no final solution. It's just a huge mess, and there are only two things that we know is that one, natural languages are capable of talking about everything. Images are the natural supplement for language whenever you're talking about spatial stuff. And then when it gets down to a computer, it's all zeros and ones, and somehow you got to relate all three of those things. That's it.
John, I want to comment. I like what you said. You said it pretty comprehensively, and what touched me was your mention of Fineman diagram.
Right.
So if anyone looks at those wiggly and continuous kind of lines in a Fineman diagram, they are having a prerequisite of knowing all about at least the elementary particle list about which Fineman is drawing these diagrams. So out of nothing in a vacuum, you have a particle production. We call it vacuum polarization. That's where from he started, and he built a whole library of Fineman diagrams, and subsequent particle physicists have built on those Fineman diagrams, including newly discovered quarks and gluons and so on. I have yet to see the Higgs as a part of that, but yes, someday it will be connecting to that, or maybe they have already, and I don't know. So what I am saying is that if I relate to Fineman diagram because I have some domain knowledge of particle physics, are you saying that all graphs, diagrams, and visual representations imply an underlying domain knowledge? And John, in particular, you are saying that that domain at least is common, what is called natural language for each community at least of users.
Well, the point that I like about language, the best description I like is Wittgenstein's. Wittgenstein started off in his first book. He was influenced by Frege and Russell, and he had a very narrow sort of logic-based view, and of everything that can be expressed in logic. And the final sentence of his book was, and whatever everything that the last part was everything that can be expressed, everything that can be said clearly, and what cannot be said, about which worauf man nicht sagen kann, darüber muss man schweigen. So if you can't say it, you must be silent. Now that was in the first book, and then in his later books he realized, then after that he started teaching children's in an Austrian mountain village, and he realized that kids don't speak in first order logic, and he realized that the way they do talk with all their fantasies and everything, he realized that you have to support an infinite number of ways of talking, that they talk in many different ways, and all of them are justified. And so his later later writings, he was emphasizing that there is no, he used the term language game, and the word game is sort of misleading. It's better to say something like language activity. And there's, for each kind of human activity, there's a different subset of language that you use for talking about it, and you can draw diagrams and pictures for those things that are have visual sort of things, or you can have music associated for things that are audio, and there's just this infinity of possible language activities, each one of which can be mapped into logic, but each one is going to be mapped into a different subset of logic. And but the one thing that is true is that you can use ordinary language in any dialect to talk about all the possible things that people can think about, because if they think something new, they just add a new word and they can talk about that. But the hard part, though, is trying to relate different languages and different subsets.
May I offer another dimension to that as well, and that is, given that if a graph is a sparse matrix, perhaps representing a domain of interest, the one thing that is fairly observable about graphs is that they are not static. Unlike the ERDs in a relational database environment driven by relational math, the advantage of a graph is that it is able to represent and to morph with dynamic change. And I know of no domain where there's no dynamicism unless that domain is just totally stayed and lost, and there are very few of those. So I would suggest that the notion of dynamics is something that is absolutely essential to any kind of descriptive language.
Absolutely, absolutely. Dynamic change is essential. The only thing that's constant is change. And the point I would simply make is, yes, you can always add another a node to a graph and a few more links. That's wonderful. But you can do the same with the table. You can always add another row or another column. And so the point is that logically, they're equivalent. And you can have a dynamically growing table in the same way that you can have a dynamically growing graph. And the difference is, but I certainly agree that there's a huge difference in the ease of changing them. And that's one.
Right. Sorry.
Okay.
Yeah. Agreed.
Okay,
Hello?
we've reached the end of the hour. How about if we're going to have to adjourn now, but let's continue this discussion next week, starting from slide 6. Does that make sense? There are more issues to discuss.
What is slide 6, Ken? Could you show us?
That's next week. Go back, Ken. Go back, Ken.
So this is slide 6, still more issues and comments. Right. I think there's a lot more to discuss, but we've captured a great deal today. It's on the recording. So I'm going to stop the recording now.